In this video, we're going to discuss some physical properties of solvents that are dependent on the concentration of the solution. As the solution concentration goes up or down, these properties change as well. Collectively, these properties are known as colligative properties, and we'll explore a couple examples of them in the slides to come. We'll begin our video today with an overview of some of the colligative property concepts we'll be discussing. First, we'll come up with a more formal definition of what a colligative property actually is. And while there are many examples of colligative properties out there, we're going to focus primarily on two of them this year, talking about boiling point and melting point. We will redefine both of those terms, although I think most of us have a pretty solid idea of what those two ideas are. We'll talk about equations that can be used to measure how much the properties change as a result of changes in the concentration of our solution. And last but not least, we'll provide explanations as to why these changes actually occur. What's happening at the atomic level in the solution that causes boiling point to change the way it does and melting point to change the way it does. Before we dive into some of the details, you'll notice some of the pictures to the right depict some things where colligative properties are actually important. On the top, we have a picture of antifreeze. Antifreeze is a solution of many different ingredients, all of which are designed to make sure that the substance doesn't freeze when it's out in your car in cold areas. If we had the liquid used to cool our cars be just water, in the wintertime it would freeze and it would cause damage to your engine, the lines and actually the engine block itself. Down below, we have a diagram of a process known as dialysis. People who have had lost kidney function in their life basically require a machine to regularly clean their blood for them, which is what the kidneys normally do. This dialysis device is based off of the concept of osmotic pressure, another colligative property, and the machine manipulates concentrations across membranes in order to pull toxins out of the individual's blood. Let's begin our discussion with a formal definition of what colligative properties actually are. A colligative property is any physical property of a solution that changes with the concentration of that solution. In your experiences, you probably already have come across colligative properties, but without the fancy name to go along with it. Some very quick and easy examples of colligative property would be things like color and taste. All of us have likely made solutions of things like Kool-Aid, where you mix a powder into a certain quantity of water. Adding more powder to the water is going to increase the depth of the color, and it's also going to increase the sweetness of the actual beverage. We would describe both of those properties as being colligative properties because they are contingent on how much of the solute you put into the solution or how much the concentration is. Looking at things more scientifically, we can also talk about properties like melting point and boiling point as being colligative properties. We can see over here on the right a diagram that hopefully looks familiar. This is a phase diagram for water. The dark blue area in the center of the diagram represents the phase diagram that would represent the pure solvent. However, what we can see here is as we've added in a certain quantity of solute, the lines separating the solid liquid phase and the liquid gas phase have shifted outward as a result of that. Looking then at this dotted line here at the top, which represents atmospheric pressure, we can see that our melting point has gone from the original melting point here to a new melting point here. We see a change in melting point difference equal to this difference in temperature. Likewise, our boiling point, which originally was at this temperature, has increased somewhat to be a new boiling point at this higher temperature. Because boiling point and melting point changed as a result of concentration, we think of them as colligative properties. Rounding out our list are a couple other properties we would call colligative properties. Vapor pressure we discussed earlier in the unit. It'll actually be talked about a little later on today as an explanation for why things like boiling point change. Osmotic pressure is another common one we won't have time to get to this year. You learned about the process of osmosis back in your freshman year in high school, the idea that liquids pass through semi-permeable membranes to equilibrate concentration on both sides. Well, the bigger the difference in concentration, the stronger that pressure is, the more the liquid pushes through. And likewise, there are many, many other options for colligative properties as well. We're trying to keep our scope relatively narrow. Let's begin then with the first colligative property we'll be talking about today, boiling point. Before we start, we'll remind ourselves what the definition of boiling point is. Boiling point is the temperature at which the vapor pressure of your substance is equal to the atmospheric pressure. Remember, vapor pressure is the natural rate at which the liquid or your solvent evaporates into the air. Atmospheric pressure is the pressure pushing back down again. When those two forces are equal, you're going to start to see a net movement of the liquid turning into the gas, i.e. boiling. Another way of describing boiling point that might be a little more useful for our conversation today is the temperature at which the average kinetic energy of your liquid molecules is large enough for them to shake free of the intermolecular forces that are holding them together as a liquid. And we often think of that model of the molecules moving around. The more they move, the less likely the intermolecular forces are going to be capable of holding them together. In short, what we can say here is that boiling point, and this is our key point on the slide here, boiling point is going to go up as a result of higher concentration solutions. So the more and more stuff we dissolve in our solvent, the higher our boiling point will be. We refer to this phenomenon as boiling point elevation. Like so many things in the sciences, we have an equation that describes boiling point elevation. This value for delta T is basically the number of degrees Celsius your boiling point is going to go up. So it doesn't tell us what the new boiling point is, it tells us how much the boiling point changes, hence the use of the delta symbol right here. K sub B is a constant value known as the boiling point constant. It's a number that relates together how much a particular solvent's boiling point changes as a result of the concentration of a solution. This is not a number that you need to know or figure out. Instead, it's a number that is typically provided for you in tables similar to the one shown down here. And I have a link for the copy of this table available linked in the page down below. The value I is another constant value, but unfortunately in this case it's one you have to figure out. This is a term we'll discuss in more detail on the next slide. And lowercase m hopefully looks familiar. It's one of our concentration units we talked about. In this case, it is the unit of molality. So you'll have to calculate the molality of your solution and plug it in right here in our equation. Now, as promised, the value I is something that requires a little bit more of an explanation in terms of understanding what it is. In terms of a definition, I is a measurement of the number of ions or particles released into a solution when the substance dissolves in water. If you think back to some of our discussions from earlier on in the unit, when a solute, such as chemical AB, dissolves in water, we can think of this as a reaction where chemical A, the first part of the molecule, in this case an ion, separates from ion B, and we end up in solution getting the separate ions as opposed to the whole chemical we normally see when we scoop this stuff out of the jar. I is designed to represent the fact that these particles separate. This is important to us because as each of these individual ions has a disruptive effect on the intermolecular forces that exist in the boiling point, something we'll talk more about in a few minutes. But since each of the individual ions has a disruptive effect, the more ions present in solution, the stronger this effect has. And that's exactly what this value I is supposed to keep track of for us. In ionic solutes, the value of I is equal to the total number of ions in the formula. For example, when sodium chloride dissolves in water, it separates into sodium ions and chloride ions. We would say in this case that our value of I would be equal to 2 because we got 2 ions from our sodium chloride. In the case of sodium sulfate, we get 2 sodium ions and 1 sulfate ion. We would say in this case that our value for I is going to be 3 to represent all 3 of those ions. Again, each individual ion has an impact on how much the temperature changes. Therefore, I is what we use to keep track of that. For ionic solutions, regardless of what your reaction is, we always expect I to be greater than or equal to the number 2. In covalent compounds, the process is significantly simpler. When covalent compounds dissolve into solution, there are no ions to separate. As a result, we only end up getting one particle, one opportunity to disrupt intermolecular forces, and regardless of your covalent compound, we always expect I to be equal to 1. So depending on whether your substance is ionic or covalent, we can use this information to determine the value of I that's going to be plugged into our equation. And we'll certainly spend some time in class practicing this skill. Now that we have an understanding of the mathematics that can calculate how much our boiling point changes, we need to come up with an explanation as to why boiling point changes as a result of concentration. This explanation is unfortunately a little bit on the complicated side and involves the use of an entirely different concept known as vapor pressure, something we discussed earlier in the year. If you recall, vapor pressure is in a closed container, a liquid will evaporate, and we can see that evaporation occurring when particles are leaving the liquid phase and entering the gas phase. We talked about this being a result of them gaining enough kinetic energy to shake themselves away from the intermolecular forces holding the liquid particles together. Well, when this starts to happen and you produce more gas, some of these particles will escape into the gas phase, but some of the gas phase particles will naturally find their way back to being in the liquid phase again. Eventually, you'll hit a point where you get basically an equal amount of particles going from liquid to gas and gas to liquid. We reach a state known as equilibrium. And the pressure that that vapor exerts when we reach this equilibrium is what we refer to as our vapor pressure. Every gas has a unique vapor pressure associated with it, and those vapor pressures are often dependent on factors like temperature. In summary, though, connecting it back to why we're trying to explain boiling point, basically what we can say here at the bottom is that when we have a higher vapor pressure, we think of this substance as being easier to evaporate, or, another word, being more volatile, something that's going to basically evaporate very quickly and easily. Water has a relatively low vapor pressure, for example, when compared to something like acetone or nail polish remover, which evaporates very quickly. Now that we've reminded ourselves what vapor pressure is all about, let's try tying it back to boiling point and ultimately to this concept of colligative properties. Something we can say, and we'll start with a couple of major ideas and then link them all together back to boiling point. The first thing we can say in terms of major ideas is that evaporation occurs uniquely at the surface of the liquid. Those particles need to escape the intermolecular forces, and the only opportunity they have to do that is when the particles themselves are at the surface. Therefore, we can say that the more solute molecules we have present, that means there are fewer solvent molecules available at the surface. You can imagine some of those spaces at the surface are taken up by the solute. Looking at our diagram over here to the right, we can clearly see in this situation, these blue circles represent our solvent. They're the ones that are trying to evaporate and exert that vapor pressure. But we can also see that at this surface here, some of the spaces of the solvent are taken up by our solute molecules, and that's not the case over here in our pure solvents. The end result is because there are fewer solvent molecules at the surface, there is a less of a chance for our solvent molecules to evaporate. The result of this is that we can say vapor pressure goes down as solution concentration increases. We expect a lower vapor pressure at higher concentrations because there are fewer and fewer opportunities for our solvent molecules to reach the surface. So again, still working towards tying this all back to boiling point, just to make sure that it's fresh in our mind. Again, vapor pressure goes down as the solution concentration increases. If you recall from earlier when we talked about vapor pressure, we talked about vapor pressure as basically being, first of all, increasing with temperature. And the fact that, and here's our key point here, the boiling point occurs when the temperature, at the temperature when the vapor pressure is equal to atmospheric pressure. So here is our atmospheric pressure, our 760 millimeters of mercury, and this dotted line represents those vapor pressures. You can imagine then, if vapor pressure goes down with increasing solution concentration, that's going to take the shape of these curves and it's going to shift them downwards. We would expect this diethyl ether line, for example, to change to look like this as a result of the increased concentration. And what we can see here is our boiling point, our temperature at which has happened here, has gone from this lower temperature on the pure solvent up to this higher temperature. We now have a boiling point closer to 40 degrees, whereas it looks like the boiling point of the pure diethyl ether was closer to 30 degrees. So we've seen boiling point increase as a result of a drop in vapor pressure. Just to put that into writing then, if a higher concentration lowers vapor pressure, i.e. creates this lower line, to put all this into words, If a higher concentration lowers vapor pressure, causing the line to drop, then we have to get to a higher temperature to have boiling actually occur, and that's exactly what we saw occur up here. We saw our boiling point shift from a low temperature, around 30, to a higher temperature, around 40. Let's continue this process with a melting point as our next colligative property. If you recall, melting point is a temperature at which the average molecule has lost enough kinetic energy so that intermolecular forces can start to fix the molecules into the rigid pattern. And if you recall from earlier in this unit, that rigid pattern is one of the key characteristics that makes a solid a solid. What we can say to summarize the pattern we're about to see is that melting or freezing point goes down as concentration increases, and we refer to this process as freezing point depression. Just like before, we have an equation that determines how much the freezing point actually changes. Delta T, again, is going to be a measurement of the degrees Celsius that our melting point is going to go down. It's not the new melting point, it's how much the melting point changes. Just like before, K sub F is a constant. In this case, it is the freezing point constant. And just like before, K sub F is not a number that we need to know. It's a number that we'll read off of a table, and this table will always be provided for you. I is the same exact term as it was before, and M still stands for your molality. So it's a very, very similar equation to our boiling point equation. The only difference is we'll be calculating how much our melting point goes down as opposed to how much our boiling point goes up. We can jump right to the explanation as to why the melting point actually decreases, because we've covered the equation enough before. Freezing of the solvent means slowing down the particles long enough, lowering the temperature, so that they can form themselves into a regular pattern, and that regular pattern is held in place by intermolecular forces. So where that freezing point actually occurs, or where that melting point occurs, is a determination of how strong those intermolecular forces actually are. When we add solute particles into the mix, those solute particles interfere with the formation of those regular patterns. Here, for example, we can see the hydrogen bonding present in water molecules, but notice by adding in these solute molecules here, some of the hydrogen bonds are interrupted. As a result of this interference, as we add more solute molecules in, we end up getting more of this interference, and as a result, it ends up being harder for your substance to solidify. There are fewer intermolecular forces there to create that rigid pattern, and the end result is we get to lower temperatures for the amount of energy to be low enough for that pattern to actually form. We get a lower boiling point, lower melting point as a result of more interference from solute molecules. So let's wrap this up. A relatively long discussion that really boils down to a couple main ideas. You should be able to tell me what a colligative property actually is in general. You should be able to explain how and why higher concentrations change boiling point and melting point. And then through processes that we'll work on in class, you'll also be able to calculate the new boiling points and melting points of your solutions based off of things like the values for K, the I you'll determine, and the molalities of your solution.